A stack is a collection that follows the last in first out rule. The element that is added last is the first one to be removed. Think of a stack of plates in a cafeteria. You always put a clean plate on top, and when you need a plate, you take the one on top. A linked list-based stack stores each element in a node that points to the next node. Because we can add or remove a node at the front of the list without moving any other element, the linked list naturally represents the last in first out behavior. This implementation is suitable when the maximum size of the stack is unknown or changes frequently. Because we do not need to decide a fixed array size in advance, memory is allocated only when a new element arrives and released when it leaves. Each node of a singly linked list has two fields. Data holds the actual value, for example, an integer, a character, or a pointer to a more complex object. Next is a pointer or reference to the next node in the chain. In memory, the layout looks like data followed by address of next. When the stack is empty, the top pointer is null. When we push a new value, we allocate a node, typically with malloc in C or new in C++ or Java. We store the value in data, set new node.next to the current top, and finally update the top pointer to the new node. Because each node is independent, the nodes can be scattered throughout the heap. The only thing that keeps them together is the chain of next pointers. Push adds a new element to the top of the stack. The algorithm performs a constant amount of work. 1. Allocate a new nodes. Procedure push open parenthesis value close parenthesis colon. New node gets allocate nodes. 2. Store the value. New node.data gets value. 3. Link the new node to the current top. New node.next gets top. 4. Move the top pointer to the new node. Top gets new node. End procedure. Step-by-step explanation colon. 1. Allocate. The runtime asks the heap for a block large enough for a node. This is an O1 operation because the allocator works on a free list. 2. Store. Writing the value into the node's data field takes constant time. 3. Link. Updating the next pointer is a single memory write. 4. Update top. Changing the stack's head pointer is another single write. Since the number of elementary operations does not depend on the number of elements already in the stack, the time complexity is O1 constant. The space used grows by exactly one node, i.e., theta 1 extra memory per push. Explanation colon pop removes and returns the element at the top. It must also guard against trying to pop from an empty stack underflow. The algorithm colons. Procedure pop parentheses to value. If top equals null, then raise underflow error or return a sentinel. Then if 1. Keep a reference to the node to be removed. Temp gets top. 2. Retrieve the stored value. Value gets temp.data. 3. Move top to the next node. Top gets temp.next. 4. Return the memory to the system. Free node of temp. Return value. End procedure. Explanation of each constant time step colon. The if test reads a pointer O of 1. Saving top and temp and reading temp.data are simple loads, O of 1. Updating top to temp.next is a single pointer assignment, O of 1. Deallocation free node operates on the node's header and is O of 1. Thus the whole pop runs in O of 1 time. If the stack is empty, the algorithm reports an error instead of accessing invalid memory, preventing undefined behavior. The memory reclaimed is exactly one node, so the net space change is negative theta of 1 per successful pop. The top/peak operation returns the value stored in the node pointed to by top, without modifying the stack. It is useful when we need to look at the most recent element but keep it for later. The algorithms. Function peak arrow value, if top equals null, then raise empty stack error, end if return top.data, end function. Only a single pointer check and one memory read are performed, therefore the complexity is O1. An empty stack test top equals null is also O1 and can be used by any client code to decide whether a pop or a peak is safe. In real life, this is like asking what's the plate on the top of the stack without taking it away. When we compare the space usage of a linked list stack with an array-based stack, we consider two aspects. Static array requires a contiguous block of memory of size n, the maximum capacity. If the actual number of elements n is much smaller, the unused cells still occupy memory. Space equals big O of n. Dynamic array vector can grow, but it usually doubles its capacity when full, leading to occasional unused slots, about 50% on average. The amortized space is still big O of n, but with a constant factor greater than. Linked list: each element occupies exactly one node plus the overhead of a pointer. There is no pre-allocation. The total memory is theta of n, where n is the current stack size. The only extra space is the top pointer constant. Advantage: the linked list adapts to any size without waste, making it ideal when the maximum depth is unknown or can change dramatically during execution. The trade-off is the per-node pointer overhead and possible fragmentation, but these are usually small compared to the waste of a large static array. Mathematically, if each node uses b bytes for data and p bytes for the pointer, total memory equals n times open parenthesis b plus p close parenthesis. For an array of capacity n, memory equals n times b when n much less than n. The linked list uses far less memory. Example expression: 512 plus 4 times plus 3 minus. Step by step using a linked list stack. Read 5 push 5 stack contains 5. Read 1 push 1 stack contains 1 and 5. Read 2 push 2 stack contains 2, 1 and 5. Read plus pop a equals 2 pop b equals 1, compute b plus a equals 3, push 3, stack contains 3 and 5. Read 4 push 4 stack contains 4, 3 and 5. Read times pop a equals 4 pop b equals 3, compute b times a equals 12, push 12, stack contains 12 and 5. Read plus pop a equals 12 pop b equals 5, compute b plus a equals 17, push 17, stack contains 17. Read 3 push 3 stack contains 3 and 17. Read minus pop a equals 3 pop b equals 17, compute b minus a equals 14, push 14. End of input. Pop the final value 14 is the result. The mathematical expression represented is 5 plus 1 plus 2 times 4 minus 3 equals 14. Each operator causes exactly 2 pops and 1 push, all O1. The whole evaluation runs in O of k, where k is the number of tokens, and the extra space never exceeds the number of operands, i.e., O of n, where n is less than or equal to k. Using a linked list stack means we never need to guess the maximum number of operands. The stack grows exactly as needed. 1 period. Prove that push and pop are big O of 1. Proof sketch: both operations consist of a fixed sequence of pointer assignments and a single memory allocation or deallocation. None of these steps depend on the current stack length, and therefore the number of elementary operations is bounded by a constant c, and the runtime t of n is less than or equal to c, which implies the runtime is in big O of 1. 2 period. Detect a memory leak in the stack implementation. A leak occurs when allocated nodes are never freed. In a correct POP, free node temp must be called for every successful removal. Also, when the program terminates, any remaining nodes should be traversed and freed. An exam may ask to write a destroy stack routine. Procedure: destroy stack. While top is not null, do set temp to top, set top to top. Next, free temp, end while. 3 period. Write complete code for a stack using a singly linked list, see style. Define struct node with integer data field and pointer to next node. Define struct stack with a pointer named top that points to a node. Function init stack sets the top pointer of the stack to null. Function is empty returns true if the top pointer is null. Function push allocates a new node, stores the given value in its data field, points its next field to the current top, and then updates the stack's top to the new node. Function pop first checks if the stack is empty and signals underflow if it is. Otherwise, it stores the current top in a temporary variable, records its data value, moves the top pointer to the next node, frees the temporary node, and returns the recorded value. Function peek checks if the stack is empty, and if not, returns the data field of the top node. Function destroy stack repeatedly calls pop while the stack is not empty, reusing pop to free each node. All operations run in constant time because they involve only a handful of pointer reads and writes, and at most one memory allocation or deallocation. Push X, allocate a node, store X, link it on top, update the top pointer. Must handle allocation failure, for example null from malloc. Pop, remove the node at the top, return its data, free the memory. Must check for underflow, top equals null before removal. Top or peak, return data from the top node without removal. Must check for an empty stack, otherwise it returns an undefined value. Empty Boolean test whether top equals null. The linked list representation guarantees that the stack can grow as long as the heap provides memory, eliminating the need for a predetermined capacity.